Hi. In this unit, we're going to be talking about the educational framework EDF. EDF is a framework implemented in Python and NumPy in about 2 pages of code. So it provides a very simple approach to understanding more of the details of frameworks and a lot of the issues that arise in dealing with them. So what's going to happen in this implementation is we're going to have our programs, our deep learning programs, written literally in NumPy Python at essentially the same level that I've been using in the notes in the units before we were talking about actual code. So your actual code is going to look just like this, very abstract assignments where these procedure calls, F, G, and H, are going to be actually classes. So this F is building an object in the class F, and its init procedure is being called on its arguments. And Y is going to be that object. Remember that when we talked about the forward and backward procedure, we talked about the variables being represented by objects with value attributes and gradient attributes. So that's happening automatically under the hood here just by letting F be a class and defining its init procedure appropriately. So we're going to have 3 kinds of nodes in this implementation. We have inputs, we have parameters, and we have computed nodes. And remember that we need to do mini batching. We're computing with batches. So the inputs and the computed nodes are representing batches of inputs and their corresponding computed node values. So the inputs in the computed nodes are tensors with a batch index. However, the parameters are the same in every batch. So the parameters do not have a batch index. And when you run the forward pass, the value attribute of the parameters and the inputs is provided, and we're computing the value parameters of the computed nodes. So here's our program. So here I'm going to take X to be an object in the class input. P and Q are going to be parameter objects. So there's going to be a general class parameter and then various subclasses of parameter for different kinds of parameter objects. So what's happening here is that Y is an object in the class F, Z is an object in the class G, U is an object in the class H, and then we're going to take a loss. We always have to have a loss to compute the backpropagation, and the loss object is going to be the same object as U. This is just Python code. Right? So here's the core of the EDF framework. We need to define a forward program, a backward program, and here we have also an SGD update procedure. So we're going to the computed nodes get collected in this list of computed nodes. And in the forward pass, we just loop over the list of computed nodes. And for each computed node, we call the forward method for that node. So every variable, every node is in a class that defines its forward method for computing its value attribute from the objects that are used as inputs to that inputs in that line of the program to compute that value. So every object knows how to compute its value from the values of its inputs. And we're just going through forward passing, computing the values of everything. Now, in the backward pass, remember that a given variable can occur in multiple places in the program. So as you go backward, you have to be adding together the gradients, the contributions to the different occurrences of that variable. So as you go backward, you're just adding into the gradients. And so the first step you have to do is set all the gradients to 0. So we say for C in the computed nodes plus together with the parameter nodes, we're setting the gradient attribute to 0. And then we initialize the loss gradient to 1. And then we loop over the computed nodes in the backward procedure. We're looping over the program, over the computed nodes in the reverse order. So we take the computed nodes and construct them in reverse order. This is the NumPy expression for reversing the order of this. And then in the reverse order, we call a backward procedure on each computed node. And that backward procedure is going to add into the gradient of the inputs to that node, pushing the gradients backward through the program. And then there's an SGD procedure that loops over the parameters and updates the parameter values according to the SGD equation with a learning rate eta, and assuming that for each parameter, we've computed a gradient. Okay, so let's just go through this still for an arbitrary sort of unspecified class F, but in sort of seeing what the NumPy Python code looks like, the EDF code looks like. So for an assignment of this form in the source code for our deep network, F is a class, so we're defining a class F, and that's going to be a subclass of computed node. And the initialization procedure for this, so when we call this F, it's going to give us a new instance of this class, and it's going to initialize it using this initialization procedure that's specific to that class. So this is specific to F. But for any class, when we build it, we add it to the global list of comp nodes. So as we build each class, just through the initialization procedure, this is being added to the list of comp nodes. It also has to remember this object, this F object has to remember P and X, because when you compute the forward value, when you run the forward program, you have to be able to compute the value attribute of Y from the value attribute of P and the value attribute of X. So it has to remember X and P. And then you have to define a forward method specific to X, and that's going to depend specific to F, and that's going to depend on what F is. So the forward method will set the value. The backward method is going to assume that the gradient of Y, the Y gradient attribute has been set, and it's going to add into the P gradient attribute and the X gradient attribute. Now, when we're coming backward, this is where Y got created. So by the time we get back to this backward, the Y gradient, even though it's only adding in as we go backward, by the time we get here, it's fully formed. It's all of its occurrences have been accounted for because this is where it was created. Okay, so there are these generic classes, high-level classes, input and comp node, that that many different kinds of computation nodes inherit from. So for an input, there's no, when we do, we don't need to initialize an input, and when we do when the add grad method is called on an input, we just pass. We don't do anything because we're not interested in the gradient with respect to the input values. For a comp node, for a computed node, when we add in a gradient, we just do the addition. And again, it's probably a little mysterious, but for people not fluent in NumPy, but all of these operations can be applied to tensors. And there's something called broadcasting that appropriately takes two tensor shapes and merges them for whatever, in an appropriate way for whatever this operation is. So this is really a tensor addition here. Parameters. So when you build a parameter, you add it to the list of parameters, and you set its value to a value. And then when you're coming backward and you add into the gradient of a parameter, you have to account for the fact that parameters do not have a batch index. So the add grad method on parameters sums over the batch index. And this is the way that NumPy sums over the first index of a tensor. And then there's this convention that you divide by the batch size. So the parameter gradients are the average over the batch. Okay, let's actually do a real deep learning, deep network. So this is the actual code for a 2-layer, multi-layer perceptron. It's this simple. As I said before, frameworks are designed to take very simple high-level code and automate the process of SGD, the forward and the backward passes. So here, I'm assuming that this phi1 is a system of parameters appropriate for an affine transformation. Now, an affine transformation is going to take this tensor, or think of this as a vector in the simple case. It's going to take this vector and it's going to multiply by a matrix to get a new vector, and then it's going to subtract a vector of bias terms. And then it's going to pass the result of that into the sigmoid function. So this is essentially the code we had before, except now it's in this notation where I'm assuming an affine class. An affine class, so we can build affine transformations in our program. Now, so we've got our first layer. This is a vector in the first layer. Then we take that first layer and we do another affine transformation. So we're calling the same affine procedure, but with different parameters and possibly with a vector of different length. So this affine, but nonetheless, when we call this affine, we're getting another node with this system of parameters and its input. We apply the sigmoid just like we did here, and then we take a softmax to get a probability distribution over the labels. And then we can call the log loss procedure to get a loss. So let's go through how we implement each of these classes. So remember that there's going to be an affine class, a sigmoid class, a softmax class. Each class has an initialization procedure and a way of doing the forward and backward. So here's the sigmoid. Here's abstract notation for the sigmoid class. So the sigmoid itself, if you go back here, the sigmoid is being applied to the result of the affine. So all the sigmoid is doing is it's applying the sigmoid activation function to each element of the tensor that it's given. So here the sigmoid is taking x as an input. X has a batch index and then an index into which vector element it is. And so we're setting the output of the sigmoid to be just the sigmoid scalar function applied to each element of this. And the sigmoid scalar function is this function. And there's this trick, I'm not going to go through the details, but there's this trick that the derivative of the sigmoid function is just the value of the sigmoid function times 1 minus the value of the sigmoid function. And you can stare at this slide and convince yourself of that. But that makes the backward computation a little bit more efficient. You can often find optimizations that make the backward computation more efficient. And so now the backward computation is going to have to add into the gradient attribute of x due to its contribution to the y value. So the backward method is going to add in the y grad times the derivative of the sigmoid, which is the y value times 1 minus the y value. And here's this implemented in code rather than in mathematical notation. So it's basically what you expect. The forward method, we add, when we construct a sigmoid, we add it to the set of comp nodes, we remember its input. The forward method just computes its value according to the sigmoid equation, the sigmoid formula. Now, it's worth keeping in mind that x is a vector. So if we take x, self.x is the x that this object is holding, we take its value, this thing is a tensor or a vector. In general, it could be an arbitrary tensor. This is a scalar function, and NumPy just knows that when it applies a scalar function to a tensor, it applies it to each element of the tensor. And plus knows when it knows that when it adds a scalar like 1 to a tensor, it adds it to each element of the tensor, and that's called broadcasting. And broadcasting has some subtleties, but generally it just does the right thing. Okay, the backward method is similar, but in the backward method, we call addgrad because we don't really know what kind of object x is here, whether it's a parameter or a input or a comp node. We don't want to make an assumption, so we call the addgrad method, and those addgrad methods are different for different categories of object. Okay, so the affine class. So one thing that's going on here is that NumPy knows how to do fast matrix multiply or fast tensor operations. The NumPy primitives are defined on tensor objects. So when I write a matrix multiply, So the affine class involves a matrix multiply, and this first line is just expressing a matrix multiply. Remember that the weight vector does not have a batch index. That's a parameter. That does not have a batch index. The x is some value that's either an input or has been computed from input, so it does have a batch index. So this affine class is assuming that the parameter has no batch index, x does have a batch index. You don't want to write this sum. Instead, you want to call the low-level matrix multiply operation. So you want to express this sum as a matrix multiply operation, which we can do this way. This one's easy. Okay, so this is expressing the matrix multiply and getting this intermediate result y tilde. Then the actual y we want from the affine transformation is the result of the matrix multiply minus a bias term for each element. The bias term is also a parameter, so it does not have a batch index. But we can just write it this way, and broadcasting automatically extends this over the batch index. So each pair bj gets the right value of the bias term via broadcasting. And then when we write out the backward method, now when I went through the backward method for tensor computations, I used this loop notation. And the loop notation makes things very easy to express and understand in terms of when you have all the indices present. But when you go to implement that in a framework, you have to translate that into the matrix operations, the tensor operations that are fast in the framework. So for example, in computing the gradient of x, you can go through the loop notation and calculate that the gradient of x should be updated by this equation, which is a sum over j. In that loop, there's going to be a loop over j, and for each element of j, we're adding into this gradient. So the gradient update involves a sum over j of this product, and I can and then what you have to do is translate this into a matrix multiply such that you can call the matrix multiply primitive that just expects two matrices without any of the indices being named. And sometimes this is tricky. So when you go to w.grad, it's easy to write this expression for what the update to w.grad should be. It's an average over the batch index of this product. And if you go through the loop notation, you can get that. But then it becomes a little bit unclear what NumPy primitive to translate this into. You have to be sort of a NumPy wizard almost to do that. So here's the affine code. So the affine is taking a parameter set system phi and an input x. It's remembering x and phi. You always do that. You always append it. You always add it to the list of comp nodes. And then we have its forward procedure expressed in terms of this matrix multiply, which we saw in the previous slide. Then we have the backward procedure. And the backward procedure here, I've written with this sort of magic incantation. I said, you can get the expression from the loop notation, but then you have to figure out what NumPy primitive to call to make that, to express that in terms of the tensor operations. And this magic code does it. I guess I won't go through the details, but you can look up what new axis does, and what this is giving you is a third order tensor. This product is going to be a third order tensor, and then the addgrad method of w, since this is a parameter, it's going to sum over the batch index as part of the addgrad method. So that sum over the batch index happens automatically whenever you do an addgrad on a parameter. Okay, another thing to recognize and keep in mind is that you're writing NumPy code, you're writing Python code, and you can write recursive procedures in Python. So I can define a multi-layer perceptron. I'm going to define a procedure that builds a multi-layer perceptron of an indeterminate depth. So it's going to take as an argument a list of parameters. this is a list of the affine transformation parameters of each layer. And there's a base case, which is if this list is empty, I'm just going to return X. But if the list is not empty, then I'm going to return the sigmoid of the affine of the first element of that list, the parameter set for an affine transformation. It's the first element of that list, and the multi-layer perceptron for the rest. So I can write this simple little recursive procedure that can take a list of affine parameters and construct an affine, a multi-layer perceptron of arbitrary depth. And that's a very powerful thing. You can write recursive, recurrent neural networks as loops. So it's built. So this procedure is building the computation graph, the program that's quite deep, but it's building it with this simple recursive call. Okay, that's all I was going to do for EDF. In the next unit, we're going to start doing vision convolutional neural networks. Thank you.